It's me, Neil, and today I'm going to be talking about the 1993 M1 question for the Physics AP exam. So in this problem, you're given two figures, figure 1 and 2. Figure 1 shows that there's a spring that is not compressed, that is not attached but touching spring, block C, which is touching block D. And in figure 2, the spring is compressed backwards by 0.5 meters. It is still not attached to block C, but it was touching it, and block B is where it remained. So that's the information that we're given. We're also given the spring constant for the spring, the mass of the blocks, and the mu kinetic friction from the block to ground. So in A, they're asking us what the elastic potential is, and that one's pretty simple. It's just you're going to plug in your elastic potential is equal to 1/2 times the spring constant multiplied by the compression squared. And plugging that in, you get 50 newtons. That one's not very difficult. B is asking the velocity just before the collision. So when this is compressed backwards, it's released and block C begins to move. So it's asking for the velocity the instant before it hits block D. So what we can do is just set kinetic energy equal to the potential and subtract that by the work caused by friction. You can't subtract it by the force of friction because it's energy, and that's not really something that you can do. But the conversion is fairly simple. For work caused by friction, it's just the mu friction multiplied by the normal force multiplied by the distance it traveled. U, we already have that, it's 50 newtons. And then kinetic energy, that one's simple, it's just 1/2 times the mass of block C multiplied by the square of velocity of C. And that's what we're solving for. So you just multiply by 2, divide by and the mass of block C, and then square it, and then you end up with 4.58 meters per second. And that's just algebraic manipulation. For C, it's asking for the velocity of C and D when they're moving together. Now it's an inelastic collision, so when these touch, they stay together and it becomes one system. And so I used momentum for this one, so I knew that the change in momentum is equal to the impulse, and because momentum is conserved, I can set impulse to 0, because the change is going to be 0. So all we have to do is just move the initial over, and then we're trying to find the final velocity, so I just divided the sum of the masses by the final, or by the initial momentum, and then I just plugged in just basic algebra, and then I got 3.05 meters per second. And then for D, it's asking us for the total distance traveled by the block system, the two-block system rather. So for that, we know that eventually it's going to be the kinetic energy minus the work caused by friction, and that's going to eventually equal 0. So we can set that to 0 and then set these equal to each other. Then after that, it's just plugging in 1/2 times the sum of the masses, because it is both block C and D, multiplied by the final velocity, which we just calculated in part C. And we equate that to the work of friction, which we already have established is the mu kinetic times the force multiplied by distance. And since we're looking for distance, we just divide by the mu of kinetic times friction. And then after that, we end up with this. You plug in your knowns, which you already have, velocity final calculated right here, the 2 from the half, 0.4, that's your mu of kinetic, multiplied by gravity. In this case, we're using 10. And we know that the whole system moved 1.1621 meters before it came to a complete stop.